For a century, neurodegeneration research has been organized by its divisions. Virologists tracking viral markers rarely converse with lysosomal biologists. Geneticists sequence genes in isolation, while matrix biology researchers publish in non-overlapping journals. Even where the molecular logic demands it, these fields rarely cite one another. This creates the century-long silence. It is the conspicuous absence of citations that should logically connect these core discoveries. This historical comparison contrasts two early accounts. In 1907, the Munich school presented an amyloid-centric model of senile dementia. Simultaneously, the Prague school described senile plaques as miliary necroses, debris fields of neurons that had died from the inside out. The field adopted the Munich model, and the inside-out framework was erased for 90 years. Modern computational synthesis confirms that the Prague model was mechanically correct. The club-shaped neurites identified in 1907 align with the 2007 ultrastructure of a panthos neuron, a cell whose lysosomes have failed to acidify, leaving it engorged with undigested autophagic vacuoles. Decades of hyperspecialization obscured this connection, allowing a terminal symptom to be mistaken for the root cause. The amyloid plaque is a late-stage artifact of the disease. This protein mass is the tombstone of a failed neuron. Removing the plaque cannot revive the dead cell beneath it. Alzheimer's represents three biologically distinct pathologies that unfold sequentially over 5 decades. Treating the condition effectively requires moving beyond single-target therapies to engage a 5-substrate architecture: the homeostatic, matrix, and synaptic mechanisms, plus propagation. The sequence begins between ages 20 and 50. The ignition point lies deep in the brainstem, specifically within the locus ceruleus and the dorsal raphe. Chronic oxidative stress here triggers PARP1 hyperactivation, which depletes the local NAD+ pool. This bioenergetic cascade operates silently, decades before the onset of clinical symptoms. This initial phase 1 collapse weakens the brain's upstream noradrenergic defenses, setting the stage for later structural failure. Between ages 50 and 70, the focus shifts to the hippocampus and the microbial network. In phase 2, mechanical failure centers on lysosomal acidification. Neurons fail to clear autophagic vacuoles and swell into a poisonous engorged state, the panthos neuron. This validates the 1907 Prague observations of club-shaped neurites, now identified as stalled autophagosomes. Secondary drivers like oligodendrocyte ferroptosis follow, forcing local microbia to transition from their homeostatic state into a destructive inflammatory state. Phase 2 marks the canonical state of lysosomal failure, where localized strain evolves into rampant cellular toxicity. At age 70 and beyond, the pathology enters the cortex. It targets the perineuronal nets that ensheath parvalbumin-positive interneurons. Microbial inflammation drives enzymes like MMP9 to digest the aggrecan and brevican matrix of these nets. This digestion removes a critical iron buffering barrier, leaving the interneurons vulnerable to oxidative stress. The loss of these interneurons destroys the brain's gamma-frequency drive, leading to the synchronization failure that causes clinical cognitive decline. The memory loss identified as Alzheimer's represents the final stage of this late-stage matrix disintegration. These 3 chronological phases are linked by transversal mechanisms, gates that pierce through the entire sequence. The first is templated propagation. Misfolded tau and alpha-synuclein are taken up by recipient cells, where they template native protein into the same misfolded conformation. This prion-like spread via the LRP1 receptor drives the Brock staging sequence and creates the progression gap seen in current amyloid-clearing therapies. The second transversal gate is the ApoE LRP1 lipid availability axis. The brain's entire cholesterol supply depends on delivery through this LRP1 receptor. The ApoE genotype sets the collapse threshold for this system. While the ApoE4 variant saturates the receptor and accelerates the disease, the ApoE3 Christchurch variant dampens binding and confers significant resistance to pathology. These 2 transversal gates dictate how and when the pathology advances through the homeostatic matrix synaptic architecture. Because the disease involves 3 distinct biological phases, monotherapies are limited to partial outcomes. This sequence demands temporal pharmacology, the deployment of specific drug classes at their relevant biological moment. In phase 1, between ages 20 and 50, PARP inhibitors like veliparib can preserve NAD+ pools to protect the locus coeruleus. In Phase 2, from age 50 to 70, ferrotoxicity inhibitors and iron chelators like deferiprone protect oligodendrocytes and halt microglial toxicity. In Phase 3, MMP9 inhibitors like minocycline are used to protect the perineuronal nets in patients over 70. These components exist today, scattered across oncological and immunological drug classes. A complete regimen also requires transversal interventions, LRP1 antagonists for propagation blockade, and isoform-selective ApoE modulators to stabilize the lipid gate. As the document specifies, this combinatorial approach addresses both the intrinsic cellular failures and the extrinsic spread of the pathology. Implementing this requires biomarkers capable of tracking the homeostatic matrix synaptic axis, rather than monitoring amyloid burden alone. Effectively addressing cognitive collapse relies on synthesizing existing literature and engineering a time-aware combinatorial defense.